Hello and welcome to all of you. Earlier in the design of rigid pavement part 1, we have discussed about the basic concepts which was considered for the analysis of stresses in rigid pavements. So we have discussed about Westergaard's analysis, in which what he has considered was the modulus of subgrade reaction we have discussed, then the relative radius of relative stiffness also we have discussed, and we have studied about the critical loading positions on a particular concrete pavement, and also we have seen the value for equivalent radius of resisting section. Now today in this video lecture we will try to discuss about the various stresses which are going to be imparted on the cement concrete pavement. Now the stresses may be due to wheel load, it may be due to temperature difference, or it may be due to the frictional forces which is being imparted because of the change in the temperature due to seasonal changes in temperature. So now let us see what are the stresses which is according to the analysis of Westergaard. Now the Westergaard's wheel load stresses, what does it define? Let us see. According to Westergaard's theoretical analysis of rigid pavement, cement concrete slab is assumed to be homogeneous, thin elastic plate with subgrade reaction vertical and proportional to the deflection. Now this is the analysis that Westergaard has adopted for analyzing the various stresses in concrete pavement. We have discussed this one earlier also, in which he has considered the concrete slab to be a homogeneous thin elastic plate, and the subgrade reaction is vertical and proportional to the deflection which is going to occur in the concrete pavement. This we have discussed earlier also. He developed equations for wheel load stresses for the three critical loading position. Now what are the three critical loading positions? We have discussed that in a concrete pavement the three critical loading positions were interior loading, then the edge loading, and the last one was the corner loading. So he had developed equation for stresses which is going to occur at these critical load positions. Now load stress sigma I or SI due to interior loading is given by, now here this is the stress value, sigma I or the SI is the stress value which is going to occur due to interior loading. The positioning of the loading is in the interior section or the interior region of the pavement. It is given by this formula, that is sigma I or SI is given equals to 0.316 times of P divided by H square whole multiplied into 4 log to base 10 L by B plus 1.069. So he has developed this formula in which our P is the wheel load in kg per centimeter square, H is the slab thickness, L is the radius of relative stiffness which we have discussed in the previous video lecture, then B is the radius of resisting section. This is also we have discussed earlier. So using all these values of P, H, L and B, we can find out the load stress which is occurring due to the interior loading. Now the next point is the load stress which is going to be occurred at the edge region of the concrete pavement. So it is given by sigma E or SE is equals to 0.572 times of P by H square, and you multiply it by the value inside the bracket. So here also P is our wheel load, H is the slab thickness, L is the radius of relative stiffness, B is the radius of resisting section. So the next point is the load stress due to edge loading. It is given by sigma C or SC equals to thrice P divided by H square 1 minus A root 2 divided by L 0.6. So here P is again wheel load, H is the slab thickness, L is the radius of relative stiffness, and A is the radius of wheel load distribution or the radius of contact area. So a particular wheel will be having a certain area of contact. The A is the value of that radius of that particular area. However, because of corner loading, tensile stress is developed on the top of the pavement across the corner bisector of the diagonal. Now here, due to corner loading, tensile stresses is going to be developed on the top surface of the pavement, which is around, in and around corner bisector or the diagonal of that particular concrete pavement. So now crack is likely to develop on cement concrete slab across the diagonal on top of the pavement surface if the corner load exceeds the flexural strength. Now the slab will be having, the concrete slab of the pavement will be having certain amount of flexural strength. Now if the corner loading exceeds that amount of flexural strength, the chance is there for development of cracks, which is going to be occur across the diagonal of the concrete pavement. So the maximum stress produced by the wheel load occurs at some distance x along the diagonal instead of occurring around the load. Now the maximum amount of stress is going to be occurred at a distance x and not around the load, and it is going to happen, or it is going to occur at a particular distance x, which is along the diagonal of the particular concrete surface. Now this distance x from the corner is given by x equals to 2.5 times of root over AL, where x represents the distance from the apex of the slab corner to the section of maximum stress along the corner bisector or diagonal. Now x is the distance which is going to be measured from the apex of the slab corner up to the section of the maximum stress, which is going to occur along the corner bisector or the diagonal of the particular pavement. Now here L is the radius of relative stiffness and A is our radius of wheel load distribution in centimeters. Now let us see a problem. Calculate the wheel load stresses at the interior, edge and corner regions of the concrete pavement using Westergaard's stress equations. Also determine the probable location where the crack is likely to develop due to corner loading. Use the following data. He has given the data here as wheel load equals to 5100 kg. Modulus of elasticity of cement concrete is given. The pavement thickness is given. Poisson's ratio is given. Modulus of subgrade reaction K value is given. Radius of contact area A is given. Now here, using all this data, we have to calculate the wheel load stresses at the interior region, edge region and the corner region of the concrete pavement. And we have to use the Westergaard's stress equations, which we have already discussed just now. And also we have to find out the probable location where the crack is likely to develop. There is nothing but the value of x that we discussed just now. Now let's move on. So the radius of relative stiffness, the value of L is given by L equals to EH square divided by 12 times K 1 minus mu square to the power 1 by 4. So you just substitute the values of E, H and K and also the mu value in this equation, and we find out the value of L, that is the radius of relative stiffness. Let us substitute this value. We substitute this value and we get a value of 70.6 centimeter, which is the value of radius of relative stiffness. Now next is the equation. The equivalent radius of resisting section is given by the equivalent value of resisting section, that is nothing but represented by small b, is given by root over 1 minus 1.6 times of a square plus h square minus 0.675 times of h. Now this equation holds true only when the a value is less than 1.74 times of h. So let's check for that. We have a by h equals to 15 by 18, which is equals to 0.833, which is less than 1.74. So we can use this formula for b to find out the equivalent radius of resisting section. That is, just substitute the values of a and h in this equation and we get a value of b equals to 14 centimeter. Now we have the radius of relative stiffness value and the equivalent radius of resisting section value. Now let's move on. In the next step, what we will do is we will try to find out the stresses due to wheel load, and we are going to first solve for the interior region. The wheel load stress at the interior region of the concrete pavement is given by sigma I or SI equals to 0.316 times of P by H square multiplied by 4 log to the base 10 1 L by B plus 1.069. Just substitute the values of P, H, L and B in this equation and find out the value of wheel load stress at the interior region. Just substitute the value. We get a value of 19.3 kg per centimeter square, which is the value for the wheel load stress at the interior region. Now the next step is wheel load stress at the edge region. The edge region formula is this. Substitute the values correspondingly and we get a value of sigma E or SE equals to 28.54 kg per centimeter square. Now we have found out the wheel load stresses at the interior region, the edge region. Now what is left out? The corner region is left out. The next step is to find out the corner region. So the wheel load stress at the corner region of the concrete pavement can be found out by using this formula. Substitute the values and we get a value of 24.27 kg per centimeter square as the value of wheel load stress at the corner region. Now we have finished 3 steps, that is finding out the wheel load stresses at the interior region, edge region and the corner region. Now what is left out? We have to locate the probable location of the crack where it is going to develop. So the location where the crack is likely to develop due to corner loading is given by the distance x of the crack from the corners of the slab is given by this formula, that is x equals to 2.58 times of root over AL, which is equals to this. Therefore x value is 83.96, let us say 84 centimeters. Now we have finished calculating this problem. Now let's move on to the next topic, that is temperature stresses. We have already discussed what are the stresses due to wheel load. Now we will discuss what are the stresses due to change in temperature. Due to variation in slab temperature, temperature stresses are developed in concrete pavement. Now the temperature of the slab will not be same all throughout the year or all throughout the day, or it will not be similar in comparison with top and bottom. Sometimes top may be having greater amount of temperature in comparison with bottom. So due to this differential in temperature across the depth of the particular pavement or the overall pavement structure, there is some temperature stresses which is induced in the particular concrete pavement. Now this is caused by, first condition is daily variation resulting in temperature gradient across the thickness of the slab. Now the temperature will be different in daytime and in the night time. So due to the daily variation in the temperature gradient across the thickness of the slab may occur. Then the another type is seasonal variation, resulting in overall change in the slab temperature. So all throughout the season, all throughout the year, there will be different seasons in which there will be change in temperature, which will in return have an impact in the overall change in the slab temperature. The daily variation in temperature causes warping stress due to temperature difference between the top and the bottom of the concrete pavement. Then seasonal variation causes frictional stress due to overall increase and decrease in the slab temperature of the pavement. So the slab will be resting upon the subgrade soil, where if the temperature of the pavement slab is changing, so it may let us suppose say that the temperature is increasing or decreasing. Due to that, the concrete will be having some contraction and expansion. So because of that, there will be some interface friction in between the bottom layer of the slab pavement slab and the subgrade layer. So due to that, frictional stresses may develop. So let's discuss further on this. So warping stress. During daytime, the top of the pavement slab becomes hot under the sunlight when the bottom still remains relatively colder, resulting in temperature gradient through the depth. Now here in daytime, the top surface of the slab will be exposed to the sunlight and the temperature will tend to rise, whereas the bottom surface will still remain colder relatively. So this will make temperature differential in between the top and the bottom, or throughout the depth of the slab, concrete slab. Now this results in expansion of the top portion with respect to the bottom. So the top portion will tend to expand more, and bottom relatively bottom will be in less degree of expansion. So the temperature differential between top and the bottom of the cement concrete pavement results in differential expansion of the slab, causing it to warp or bend. So here, due to the temperature differential between the top and the bottom, the pavement results in differential expansion of the slab. So the top portion may be expanding more, or the bottom portion will be expanding less. So due to this nature of the expansion, the slab tends to warp or it tends to bend. As the warping stress is resisted by the self weight, flexural stresses are developed at the bottom of the slab at the interior and edge locations, where this warping is actually resisted by the slab self weight of the slab. However, due to this, flexural stresses are developed at the bottom of the slab at the interior and the edge locations, and at the corner of the slab tends to warp downwards, and this is resisted by the subbase. So the tensile stress is developed at the top in the corner region. The flexural stresses developed due to temperature differential and warping of the slab is termed as warping stresses. So you need to remember this particular definition, where the flexural stresses developed due to temperature differential and warping of the slab is termed as warping stresses. So the warping stresses formulas at the interior, edge and the corner region is given as follows. First, it is for the interior region. This formula, we can use this formula to calculate the warping stress for the interior region. where Cx and your Cy will be the coefficient of warping stress. This will come up later. Let's discuss furthermore. Then in the next one is for the edge region. You can use this formula to find out the warping stress at the edge region, and this is for the formula for finding out the warping stress at the corner region. Now, what are the values? What are the notations here? Here, capital E is the modulus of elasticity of the concrete. Small E is the thermal coefficient of concrete per degree Celsius. Then T is the temperature differential between top and bottom. What is the difference in temperature? That is the T. Then Cx is our coefficient in direction x, which depend upon the ratio Lx by L. Now here Cx is nothing but your coefficient of warping stress, which you can find out using another chart which is known as Bradbury's warping stress chart, in which for different values of Lx and Lx by L or Ly by L, you can find out the values of Cx and Cy. So now what is Lx and L? Lx and Ly are the length and the width of the slab along direction x and y. So Cy is again coefficient in direction y, which depends on the ratio of Ly by L. Mu is the Poisson's ratio. Then L is the radius of relative stiffness. What is Bradbury's warping stress chart? So this is a typical Bradbury's warping stress coefficient chart, with in which for different values of the ratio Lx by L and Ly by L, you can find out the corresponding value of Cx and Cy. So the x-axis represents the ratio Lx by Ly, Lx by L and Ly by L, and the y-axis represents the values of the warping stress coefficients Cx and Cy. The values of the warping stress coefficient Cx and Cy are found out using Bradbury's warping stress coefficients chart given in the figure. The values of Cx and Cy is taken from the chart depending upon the different values of the ratios of Lx by L and Ly by L respectively. Now let us see a problem to find out the temperature stresses. Determine the warping stress at interior edge and the corner of a 25 centimeter thick cement concrete pavement with transverse joints at 5 meter interval and longitudinal joints at 3.6 meter interval. The modulus of subgrade reaction is 6.9 kg per centimeters cube and radius of loaded area is 15 centimeter. Assume maximum temperature differential during day to be 0.6 degree per centimeter thickness. Now here the temperature difference during daytime is 0.6 per centimeter thickness, which is for the depth of the particular slab, and the maximum temperature differential of 0.4 degrees Celsius per centimeter thickness during night. This is for the warping stress at the corner. The previous one was for the warping stress at the interior and the edge. So this both 0.6 degree is going to be used for calculating the interior and the edge portions only, and 0.4 degrees Celsius is going to be calculated for the warping stress at the corners region. Now here we have to find out the warping stress at the interior edge and the corner. The slab thickness is given, and also the pavement has a transverse joint that is at an interval of 5 meter, or let us say 500 centimeter, which is in the transverse direction. So we will take that one as the x direction, and 3.6 meter interval we have a longitudinal joint. So this is going to be taken as the y direction. So from this we are going to see what is Lx and Ly. So another few values are given, that is the value for E, small e, then capital E, and the mu also given. Let us try to solve this problem. Given we have slab thickness, modulus of elasticity of concrete, Poisson's ratio, radius of loaded area, then the thermal coefficient of concrete also given. Now Lx is 500 centimeter and Ly is 360 centimeter, which is nothing but the interval for which the transverse joint and the longitudinal joint was given in the slab. So slab will be continuous. So for what distance you are going to take, should be calculated using the Lx value and the Ly value, which is nothing but the interval in between the transverse joint and the longitudinal joint. So the temperature differential between T1, which is going to be used for the edge and the interior portion, is 6 degree per centimeter thickness. For every centimeter there is a temperature difference of 6 degrees. Now what will be the value of T1? Total T1 is equals to 6 into 25, which is nothing but your pavement thickness. So the T1 value is equals to 15 degrees Celsius. Likewise, the temperature differential between night time is 0.4 degrees Celsius per centimeter thickness. Just multiply the value of the temperature with the pavement thickness, you get the value of temperature differential T2 equals to 10 degrees Celsius. Now we have all the values. Now let's try to solve further. Next, let us calculate the value of radius of relative stiffness. Now what is the value of radius of relative stiffness? L is given by this formula. So you just substitute the values and you will get a value of 87.23 as the radius of relative stiffness. Then the ratio of Lx by L is equals to 500 by 87.23. Just find out this ratio. It comes up to be 5.73, and the ratio for Ly by L is equals to 4.13. Now we have the value of Lx by Ly ratio and Lx by Ly by L ratio, so we can find out the warping stress coefficient also. So the calculation of Cx and Cy, that is the warping stress coefficient. For this calculation we will use the Bradbury's stress chart. Let us refer the Bradbury's chart for warping coefficient. So this is the Bradbury's warping stress coefficient chart, in which we are going to use for different values of the ratio of Lx by L and Ly by L to find out Cx and Cy. So now let us see the value of value of Cx corresponding to the value of Lx by L equals to 5.73. So where is 5.73 in the x-axis? Which is somewhere here, which comes up to be up to here. So correspondingly the value of Cx will be here. So approximately or up to certain extent it is equals to 0.88. So therefore from chart the value of Cx is equals to 0.88. Likewise we will find out the value of Cy also. Now let us see the value of Cy corresponding to the value Ly by L equals to 4.13, which is somewhere here. Then it comes up to here. Then correspondingly the value of Cy will be 0.54. Therefore from the chart Cy value is 0.54. Now we have the value of Cx and Cy also. Now we can find out the warping stress value of the warping stresses. So warping stress at the interior part of the slab during day is given by this formula. So now in this particular formula the value of small t will be equals to T1. So it is already mentioned in the question as this particular for finding out interior part, we have to use the temperature differential was around 0.6 degree per centimeter thickness of the slab. So the T1 value was 15 degree. Just substitute all these values, it comes up to be something like this, and we get a value of 22.12 kg per centimeter square for the warping stress at the interior part. Now for the warping stress at the it should be edge part, sorry, it's written as interior. So now for the edge part, it is should be cx et by 2 or cy et by 2. Now which one you have to take? So for the value of stress coefficient or the warping stress coefficient cx or cy, which one is bigger, which one is maximum? We have to use that one in as a formula for finding out the warping stress at the edge part. So the higher value of the two warping coefficients will be taken, so we will use this formula. Here again, this is for the edge portion, so the value of T will be equals to T1, which was 15 degrees Celsius. Substitute these values and you will get the value of sigma TE or the warping stress at the edge portion as 19.8 kg per centimeter square. Now the next portion left is for finding out the warping stress in the corner region. So corner region is we are going to use for the during night time is given by sigma TC or STC E capital E small e T divided by 3 1 minus mu root over A by L. Here again this is for the night time, during night time, and question it was mentioned as the value of the temperature differential should be equals to the 0.34 degrees Celsius per centimeter thickness of the pavement. So the value of T is equals to T2, which was 10 degrees Celsius. Substitute the values in the formula, will come up to be this like this, and the value for the warping stress at corner region sigma TC is equals to 4.878 or 4.88 kg per centimeter square. Now we have found out the warping stresses, all the values of the warping stresses at the interior, edge and the corner portion. Now what is left? So the next portion that we are going to discuss is frictional stresses. So we have discussed about the warping stresses due to the temperature differences in the daily basis. Now this is for the frictional stresses which occurs due to the seasonal difference in the temperature. Due to seasonal temperature difference, there is overall expansion and contraction of the slab. Then however, the slab is in contact with the supporting layer below the slab layer, which is thus restrained by the frictional force in between the bottom of the pavement layer and the supporting layer. Now the slab will be supported by the subgrade portion. If the slab is relatively moving or it is relatively having some kind of expansion or contraction, it will be restrained by the frictional force in between the bottom layer of the pavement and the supporting layer, which is the subgrade layer. So some frictional stress will be developed. The frictional stress in kg per centimeter square is given by the equation, square is missing. Sigma F or SF is equals to WLC by F, WLCF by 2 into 10 to the power 4, where F is the unit, W is the unit weight of the concrete in kg per meter cube, which is around about 2400 kg per meter cube, and the F is the friction coefficient of the subgrade or coefficient of subgrade friction, or the coefficient of friction at the interface, which is in between the bottom layer of the slab and the subgrade surface. So this is maximum value is up to around 1.5. Then LC is nothing but your spacing between the contraction joints, or the slab length in meters. It's called as slab length in meters. So now frictional stresses also is over. We have discussed about the uh, wheel load stresses, then stresses due to temperature, and again in stresses due to temperature, it was divided into two portions where we have the warping stresses and the frictional stresses. So all these combined, we will have some critical stresses. Let us discuss about that. Combination of stresses. So the cumulative effect of the different stresses give rise to the following three critical cases, in which the case one is summer midday. The critical during summer midday, the critical stress for edge region is given by. So now the critical stresses in the summer midday will be developed in and around the edge region. So, and it's given by the formula critical stress equals to sigma critical equals to load stress plus the warping stress minus the frictional stresses, which is equals to sigma E plus sigma TE minus sigma F. And in the next case, winter midday, the critical combination of stress is for the edge region again. So in the winter midday, again the combination will be around the edge region, and is given by the formula, that is sigma critical equals to our sigma critical equals to this thing, load stress plus warping stress plus frictional stress. And the next critical case is during summer midnights, the critical combination of stress is for the corner region. So the critical combination will occur in around the corner region only. So here the critical sigma critical is given by load stress plus warping stress. Therefore sigma critical equals to sigma C plus sigma TC. So with this we come to the second portion of the design of rigid pavements. So thank you everyone, and we will come to meet in the next video lecture, and I will try to bring out some other important points in the next video lecture. Thank you for listening.